university. Whether that time has already passed and I'm now eating into my talks time, but I don't mind cutting into my talk a little bit. I do want to mention that my days at the university Kalina campus were among the happiest. And indeed, that's where I met Sonal, my wife, and we studied together. And we were taught by Professor Rangwala, Professor Arvind Kumar, Dr. Rohini Godbole, uh, Dr. Kulkarni, and Dr. Anil Pradhan. And I have to say that this time of my life, this is the time I would say, I first got introduced to physics in a very serious way. And this is the first time I actually got to see some real teachers, because before that, most of the time I was essentially teaching myself, and including at SIS college. I hope nobody from SIS is signed in here, but I did not find the physics education there particularly, uh, inspiring enough to me. So indeed, during my summer vacation time, in particularly third year of my BSc, I actually fortunately was able to join TIFR as a visiting summer research student. And there I met many scientists. And of course, that is where I first saw Professor Chitre and Professor Narlikar and so on. And in fact, I had read Professor Narlikar's book called The Structure of the Universe, which I still think is one of the outstanding introduction for undergrad students. Um, my mentor at TIFR was Dr. S.P. Tarafdar, who sadly passed away quite early age. And I got introduced to atoms and molecules in space by Dr. Tarafdar. So he also introduced me to some very nice books, like books by Spitzer. And the subsequent years, I worked again as a visiting student there with Dr. Stephens, who was working on cosmic rays, and Dr. Jit Kembave, and many TIFR people went to Ayuka. And then in university, I I really got more interested in physics, and I was thinking that I probably will not do astronomy as a career. And with that intention, I applied to Indian Institute of Science, uh, and I was admitted in the physics research program along with Sonal. We both applied, and we were both actually going to join the physics department. She, in fact, joined the physics department there, and I was about to join and accept this physics department. I had passed through the interviews there, and then they had a bunch of other interviews going on. They said there's time, if people are interested, you can sit in for this joint astronomy program interviews. And I said, okay, the day has been long. What does it matter? Just let me sit for those interviews also. So I was selected for the astronomy program as well. And then I had to decide whether to do the astrophysics or the physics program for my PhD. And the thing that attracted me for the joint astronomy program was that it was between TIFR and RRI and PRL and many institutes, 5 or 6 institutes in India, all over. And it just seemed like a very attractive option that I could go to one of these places. The other attraction was that there was a new telescope coming up at Raman Institute. And eventually I decided that, okay, let me do the astronomy. So that's how I joined. I remember my interview panel, N. Kumar, Vijay Kapai, Rajaram, Nityananda, and later on some of them became my teachers. So that's basically the short summary of the beginning. And I have to thank all of these people. But of course, teachers are not the only thing. You also make friends during all this part of the career. And at the university, I made a friend, Gurunandan Bhatt, who was Rangwala's student. And we are still friends. And, I've learned a lot from him. And similarly, at Raman Institute, I have so many friends and teachers I'm in touch with. Shukre taught me interstellar medium. Vishara taught us general relativity. Bala Iyer, who was in fact also from the university. We used to hear about Bala from, for example, from Kulkarni. Rajaram is one of our teachers. It's really been a great privilege to have gone through these people. So the talk today is on molecules, and Professor Chitre has given a very nice introduction already. But let me try to also begin with a sort of historical overview. And I will talk about molecules and dust in various astrophysical sources. This is the general outline of my talk. The reason why telescopes, methods, laboratory work is in brackets here is because this is not like a separate section. This is a continuous thread running through my talk because that's basically most of my work. The image that you're looking at here is the view of the submillimeter array, which I've been involved with since last 25 years or so. We built this array starting from 1994. And you can see the array is located near the summit of Mauna Kea mountain, about 14,000 feet altitude. And there are a number of other telescopes you can see here. This is the James Clerk Maxwell telescope. And this is the Subaru telescope. This is a laser beam going from one of the optical telescopes, the Keck telescope. They use it for adaptive optics. This is a picture I took a few years ago when I was observing at the SMA. And this is the spectacular view of the Milky Way and the clear sky. You can see some of the interstellar dark clouds here. And here I have listed many of my colleagues, collaborators, my mentors, but not, okay, I'm sorry, this is, I don't know where this line came from. Let me stop the share and start again because okay, that's better. So the historical overview, I would like to begin with Cecilia Payne-Gaposchkin, who submitted her PhD thesis to Harvard in 1925. And her thesis is considered to be one of the most brilliant PhD theses ever written. It is in this thesis that she showed, by applying the Saha equation, the Saha theory for ionization, that hydrogen and helium are indeed the most abundant constituents of stars. And at that time, there was a lot of opposition to this from experts of that time, including Russell, who was one of the thesis examiners for her. And the reason why there was this opposition is that the general idea was that whatever abundances that you see of elements on Earth would be also the same in stars. It's simply the hotter temperature. But by applying this correct theory, the data were interpreted in a correct way, and she came to the correct conclusion. And here is a picture of some of these great physicists, Meghnad Saha, Jagdish Chandra Bose, and S.N. Bose. Subsequently, we learned about hydrogen, not just in stars, but in the interstellar medium and throughout the galaxy. It was actually quite clear in the late 40s, soon after radio astronomy started at Bell Labs, that it is through radio waves that we will be able to probe the deep disk region of our galaxy. With optical, we are only sampling a very narrow, small volume of stars in our neighborhood. The Dutch astronomer Jan Oort recognized this, and he asked his PhD student, Henrik van de Hulst, to calculate the frequency of radio waves that will be emitted by hydrogen. So that is done by this so-called spin flip transition, when the proton and electron spins are either parallel or anti-parallel. This is discussed in, for example, Feynman Lectures, Volume 3, or any standard textbook in quantum mechanics nowadays. But those days, this was a research problem. And at Harvard, Edward Purcell got interested in this problem, and he was an expert on instrumentation and experimental physics, as well as theory. And he had a student, Harold Evans, so they built this setup of a pyramidal horn, which is sticking out of the physics department office on Oxford Street in Cambridge, in Massachusetts, at Harvard University. And inside, you have this waveguide bringing in the radiation, and you have all these electronics here to receive this signal at the frequency of 1.4 gigahertz. And this is their record of the detection. The reason you see this positive and negative is because they were doing frequency switching, which means you observe at some frequency and then at a slightly different frequency and subtract the two signals to cancel the common drifts to increase the signal contrast. This technique was actually invented by Robert Dicke, another great physicist around that time. And this discovery was made in 1951, which opened a pathway to our mapping of the galaxy and the galactic structure. Soon afterwards, many telescopes started surveying the Milky Way at this frequency. And my PhD advisor, Professor V. Radhakrishnan, RAD, we used to call him, was working with John Bolton in the late 50s at Caltech, where they had built this Owens Valley 2-element interferometer, each antenna of 90 feet diameter. That's shown here. And Bob Wilson and Dave Morris were also students at the time. And they were all pioneers in making this very first large-scale maps of the Milky Way. But specifically, RAD had this very interesting and brilliant idea of using interferometer to find absorption lines in hydrogen emission. This was a little different from just observing emission lines. And in this technique, using the fact that the interferometer filters out the continuous kind of extended emission, enhances the smaller angular scales, they were able to actually measure some of the very first measurements of actual interstellar clouds. So that concept was a theoretical concept, but it was measured for the first time. Now, molecules like CH, CH plus, and CN were actually discovered in the 40s by optical spectroscopy. And here is an example from an article by one of the great scientists in this field, Gerhard Herschberg. And it is showing this spectrum of CN. The interesting thing about this is that there are these two absorption lines. From the ratio of these lines, you can infer that you cannot explain this radiation, these intensities or these ratios by just considering collisional processes. You have to include some radiation field. And it turns out to actually explain this, the authors of this paper, although they didn't understand this, they put in this ad hoc parameter that you need some radiation corresponding to about 2.3 Kelvin. So of course, now we know later on from discovery of the cosmic microwave background by Penzias and Wilson, I will actually show that a little later. This is very close to the 2.7 K background radiation. But this discovery, if the analysis was pushed through a bit more aggressively, more lines of sight and more analysis, for example, then CMB discovery could have happened decades earlier. It's a very interesting point, I find. So moving on, another great scientist in this field is Professor Lyman Spitzer. I already mentioned his name a little earlier. And he was one of the first scientists to actually observe molecular hydrogen in absorption. Molecular hydrogen is the most dominant, but it is hard to observe because it doesn't have a dipole moment and it doesn't emit radio waves. Now, later on, Charles Townes is the pioneer. He's the man to really bring the idea of radio astronomy to go after molecules. And he actually predicted theoretically several molecules that can be discovered by radio astronomical methods. And he had a student, Arno Penzias, in Columbia University, who was actually appointed to follow up on this work. So Bob Wilson, I mentioned, was at Caltech after his PhD. He joined Bell Labs along with Arno Penzias. And indeed, this was actually one of their main topics of research, supposed to be, to look for molecules. Now, Charles Townes is, of course, very, very famous for his work on masers, but also this great textbook, which is sort of standard reference book for us in microwave spectroscopy. And if you want to learn about microwave techniques, the first couple of chapters of this book are actually quite phenomenal. Charles Townes also is a pioneer in infrared interferometry. And in fact, he discovered the Sagittarius star source at the center of our galaxy, which is one of the black hole candidates. So radio discoveries of molecules followed very quickly after the pioneering work by Charles Townes. In the late 60s, a bunch of other molecules were discovered. One of the most important one is water. So this is water discovered at 22 gigahertz with the so-called maser amplification process, where the population level is not following a thermal distribution or Boltzmann distribution, and you have some couple of levels which have inverted population. Upper level has more molecules. And then along some preferential path in the cloud or in the interstellar cloud, by chance you could have amplification of this gain. And that's how this bright emission can be detected. The other point is that this particular transition or energy corresponding to this transition is significantly higher, is varying hundreds of K. So the water in our own atmosphere actually doesn't absorb this radiation. So that's an interesting point. So this discovery was enabled by that. As I will mention later, uh, to observe water, you have to go either to very, very high elevation. In fact, we built the submillimeter array at the high elevation to get above most of the moisture in the atmosphere. But the real turning point in radio work on molecules came in 1970 with the discovery of uh, interstellar carbon monoxide. This was predicted by Charles Towns earlier, and the theoretical calculation of the frequency of the fundamental J equals 1 to 0 transition of rotational transition, that it should happen at 115 gigahertz or corresponding to 3 millimeter wavelength. That was known, but the technology was not there. The detector that will work at this frequency was not yet built. That was built for the first time for this particular observation. And that is why it is a very important discovery. And these slides are from Bob Wilson. Um, he has given talks on this discovery of CO at CFA and other places. This is the telescope that they used. It's the 36 feet telescope in Kitt Peak, Arizona, NRO. And this is their observation of the first CO line from Orion. For students, I would actually recommend they find via Google or something this talk. You may find YouTube or even the slides. It's a very, very exciting thing to hear about this discovery. And again, just like following the hydrogen story, for carbon monoxide, again, we started doing the surveys with various telescopes. And here I'm highlighting the telescope, which is right on our building, one of our building rooftops at the Center for Astrophysics in Cambridge. So there is that dome, which you see here. And it's a 1.2 meter diameter radio telescope, which was built by Patrick Thaddeus, and who passed away a few years ago, and Tom Dame. So Pat Thaddeus is one of my main collaborators at CFA. I work. In fact, I've been doing a lot of molecular astrophysics work, mainly thanks to him. So this is the map of CO emission in our galaxy. This is not possible to make just with one telescope. You need one more in the southern hemisphere. So there's a copy of this telescope in Chile. And it's a remarkable telescope because relatively low cost, but many PhD students have worked on their thesis just from this instrument. And even now it's working every day. They are observing, and they are now observing other molecules and also doing survey of the Andromeda galaxy, for example. And indeed, not too long ago, few years back, a new spiral arm in our galaxy was actually discovered by Tom Dame and Pat Thaddeus using this telescope. So I mentioned that a lot of survey type of projects were happening. But the interesting thing is that this actually opened a new field. It was a really big shift in radio astronomy, that we can do millimeter wavelength observations and observe many molecules, because all of these rotational transitions from various molecules, they fall in this frequency range of tens to some hundreds of gigahertz. And about 2 years after CO discovery, And HCO plus was discovered almost soon after CO. A bunch of other molecules were discovered, are listed here. SiO molecule was important because uh, it is a tracer of dense gas around evolved stars. And it also shows this major phenomena. In fact, my PhD thesis was on SiO measures. And I learned a lot about this phenomena from Shukre at RRI when I was a PhD student there. And at RRI, we built a telescope, 10.4 meter telescope, which was actually a copy of this telescope shown here, which is Caltech Submillimeter Observatory. And this CSO telescope is also close to our SMA submillimeter array on Mauna Kea. And this was built by Robert Layton. He's one of my heroes. So Robert Layton, some of you will recognize that he's the second author in this Feynman lectures series. And he also wrote a book on modern physics. We enjoyed reading parts of that when we were MSc students. And this design of this telescope is absolutely fantastic. And I learned a lot about radio telescopes in general following his work and following the work that we did at Raman Institute, building a copy of this telescope. Now, here is another one, Bell Labs 7 meter, which Bob Wilson built. And that has done some great surveys of Orion region. Here is ERAM 30 meter telescope, which did a lot of molecular line surveys. Sorry, this thing has happened again, and I will go back to my talk. Oh, annotation tools. I see. I don't know how to do that actually.
So we have done that, so you can continue with the presentation maybe.
You're seeing it, right? The screen?
Yes.
Okay. So the millimeter and submillimeter astronomy, and particularly these so-called line surveys, where you observe very large range of frequencies over a given direction or given object, you can discover many molecules. And this has opened up the field since last few decades, and astrochemistry has really come along now. There are more than there are 170 molecules listed here, 174 molecules, but there are probably close to 200 molecules known in space now. And now I'll just talk a little bit about these molecules, and particularly the role of dust and what is the story there. So here is a picture of an interstellar or interplanetary dust particle captured by a high altitude plane. And it gives you the scale of this size of these particles and this amorphous kind of nature. But the constituents of these particles is actually still a topic of research. And we are interested in finding how these dust particles are actually formed. So we believe that they are formed from tinier seed, so-called seed particles, which could in fact be formed from even diatomic molecules like SiC, for example. So SiC is carborundum. It's very hard substance. And SiC, we have discovered around these evolved stars, the circumstellar envelopes regions. And those kind of particles could be going out into the interstellar medium. And by processes leading more chemistry happening on the surfaces of these grains, more complicated uh, dust grains could be forming in these dense regions. So this is a picture of one such region where very cold and dense environment, where both organic molecules, complex molecules, as well as dust particles could be evolving and forming. This is a picture of one of these evolved stars I was talking about. This is a famous star called IRC 10216, discovered by actually Robert Layton's survey at 2-micron infrared wavelength. It's also called CW Leo. And this is the star you cannot see here, but the structure that you see here is corresponding to matter which has been expelled from this star's envelope, which is in concentric kind of shell. And we mapped this with our submillimeter array. And these are some images of the CO emission, CO221 emission, mapped with both the submillimeter array and later on with a much larger array called Atacama Large Millimeter Array. So you can see various scales zooming into the star. And these concentric shells, you actually cannot explain that by just the periodic pulsation of the star, because the pulsation period is only about 2 years. But the spacing between the shells and the velocity is suggesting that the time scale is more like a few hundred years. And so we believe that this is caused by a binary star, which is perturbing the mass loss process around the star. So we have studied this star very extensively with a submillimeter array, and we have discovered many new lines. This is an example of sodium chloride, just common table salt molecule from our line survey. One of the questions is, interesting question is how this kind of nearly spherically symmetrical envelopes turn to this more evolved planetary nebulae, which show much more complicated structure. So that process is not well understood. And we are also interested in tracing how the chemistry itself evolves, what different types of molecules are found in planetary nebulae. And indeed, when the central star in the planetary nebula becomes the white dwarf and starts ionizing the gas, what molecules will survive and finally go into the interstellar medium? Those are all the topic of research that we are currently doing with the submillimeter array. So here is an example of one such object called CRL 618. And we carried out a line survey covering many tens of gigahertz span. And the reason for doing this wide range of frequencies is that it helps you to identify molecules. So for example, formaldehyde molecule has predicted transitions occurring at this frequency labeled here by these red segments. So when you see all of those lines in your survey, then you can not only identify that this is formaldehyde, but you can also model, you can also use this information to derive physical conditions. Another example is methyl cyanide. So you see a bunch of these lines, again, repeated over this kind of frequency range. So this is just a glimpse of some of our data. It's showing you the spectral lines. And, you know, they say that a picture is worth 1,000 words, but a spectrum is actually worth 1,000 images. And indeed, when you map with interferometer, every line that you see actually has an image. It's basically a stack of images, and you can make spectra at different directions. And this is an example of the image of the cyanide molecule. You'll see that as you go across the frequency range, because of Doppler effect, the emission appears to have a different structure. And that is actually telling us about the geometry. So this is an expanding shell around the star, which appears like a ring when you look at the velocity slices. And from those multiple lines that you observe, when you apply the Boltzmann's formula for the thermal distribution of the population level per energy, so you have e to the minus h nu by kt factor for lower and upper energy levels. And you take log in this formula, and then you get a straight line. So the inverse of that is slope is directly going to give you the excitation temperature measurement. So that is what is shown here in two of the molecules. And the intercept on the y-axis will give you also the population, the column density, how many molecules are there. So this is work that we are currently involved in, identifying different molecules, also observing some ionized hydrogen recombination lines. And the general picture is that there is a sort of recycle process going on. You have stars which evolve into this planetary nebulae, and molecules are then added to the interstellar medium, and they form more complex molecules in colder, denser regions. And then stars form from that, including planets, planetary disks. And planets like our own will also form from that and get some of those molecules. And then there is a story about the comets, which are sort of remnants coming from the outer parts of such a solar system. And added along with this is the story, parallel story about the dust grain. The dust is important because even to form the simplest molecule, molecular hydrogen, the gas phase reaction is much, much less efficient and doesn't work in interstellar regions. And you need the dust grain surface. So you have hydrogen atom sticking to the grain, another atom comes, and then they stick together and they get liberated. So this process happens for many molecules, including complex molecules, organic molecules. And there is also chemistry related to the ice forming on the dust grain. One interesting aspect is that of the carbon molecules. So we have seen many long chains of carbon, and these actually could be forming more complicated structures. And in fact, now C60, the fullerene molecule, so I have a model of this here. This is made entirely of carbon atoms. That is discovered in space now. Harold Kroto is a chemist who got the Nobel Prize for his work on the C60 molecule. Here are some standard other diatomic molecules and other interstellar molecules. And the organic molecule story is also very, very interesting, particularly because we know since the time of, in fact, Schrodinger first pointed out that molecules might be the source of carrying forward the genetic information, because he showed that molecules would be strong enough to remain as singular units, because you cannot easily dissociate these molecules. So you could literally form the building blocks. This idea originally came from Schrodinger, actually. And of course, that is a topic of active research. I want to show one example from GMRT here, from Chengalur and Kanekar, of CH3CHO molecule near this black hole source in the center of our galaxy. And another example of a very complex, complicated molecule, urea. This is NH2CONH2. This is of great importance in biology. So this was discovered recently using the ALMA. And now I just quickly want to show you some pictures of laboratory work. So this is the Harvard Spectroscopy Lab. where we carry out the chemistry inside cells like this, which is relevant for example, environment around the lake type stars. And then we do absorption spectra. Um, so that kind of work has been ongoing since a long time at Harvard. And now there is a new lab by Karin Oberg, who works on the grain ice chemistry. These are some of my collaborators and friends, Ken Young, Michael McCarthy, Carl Gottlieb, and Damien Kokin, who was a PhD student. And this is the submillimeter array picture again, which I showed before. And this is the picture of the Atacama large millimeter and submillimeter array in Chile, which is many, many more antennas, each twice the diameter of SMA, 12-meter diameter antennas. There are more than 60 antennas. And just a quick note about interferometry. So this is a letter which was published in Physics Today some time ago, which illustrates the phenomenon of this coherence in the ripples in these waves, even though you start with a sort of random perturbation. So let me try to show this. This is from the picture. Yeah. So even though this is a very chaotic kind of activity going on, but after a while, you see there's a very nice ripples further along. And if you're, for example, sitting at the bank somewhere here, and you observe these ripples approaching you, you will actually find two nearby places. There is actually good correlation in the ripples that you are seeing. Okay. So this is what we do when you are doing interferometry. Is what you are measuring is the electric field at each telescope, and you are looking for these correlations. And when you find the correlations, and we call it the visibility, you measure it over different pairs of these antennas with different geometry because of the Earth's rotation. So this is called aperture synthesis, this process. It's a Nobel Prize winning idea. You know, Martin Ryle thought about this in Cambridge. And when you have a lot of such measurements of these so-called visibilities over time, you can then take a Fourier transform of this and you get the image. That's the basic idea. And the angular resolution corresponds to the wavelength divided by the maximum, the longest distance between the antennas. Just as the angular resolution for a single telescope is given by the wavelength divided by the diameter of the telescope. And so that's the general idea behind interferometry. And that's what has enabled, for example, us to do the hydrogen absorption line that Rad did many, many decades ago. That's what has enabled us to look at smaller stars and envelopes of stars, which are really very, very small in angular size. And that is what has enabled the black hole image, the most latest advance. I should go a little fast because I may be running out of time, but I want to quickly mention the role of comets. So one of the really outstanding question is, where did the water come from on our planet? And one of the hypotheses, theory, is the water was brought in later after the planet was cooled down, the rocky terrestrial planet was cooled down. The water was actually delivered later from the regions which all still have ice water surrounding the protoplanetary disks in the outer part of the disk, and that's where the comets come from. And the comets were bombarding the planet over hundreds of millions of years or billions of years, and they have delivered the water. So this is a picture I took recently of the new comet, Comet Neowise. Here's the water reflection. And how do we test this idea? So of course, first you have to detect water. So here is the detection of water at infrared wavelengths from comet Hale-Bopp. And we know that comets are actually crashing into planets. We saw that happen sometime in mid-90s. So this is an example of this happening on Jupiter. So this is a HCN molecule, which is not normally present on Jupiter. It's actually not predicted in the Jovian atmosphere chemistry. But HCN was detected after the comet impacted. So these are observations with the submillimeter array. Our friend Mark Gurwell is involved in this. And then the comets, how to check whether water is coming indeed from them is by using the ratio of D to H. Now, this is something that you can use as a probe by comparing the various other comets as well as Earth's ocean water and the solar value. And this is still a topic of research, but it seems like the Earth's ocean water was not delivered entirely by comets, but it could also have come from asteroids from outside the main belt. This is now coming towards the end of my talk. I want to show you one or two pictures from Greenland where I've been spending a lot of time. And here I see water in all three phases, ice. And what you're looking at here is the so-called Rasmussen Glacier. This is actually a region where there are 3 or 4 glaciers. And it's actually the world's largest ice factory. So these icebergs are launched from this glacier continuously. And I really love seeing these animals, these muskox. These animals are found only above the Arctic Center. So we work at the telescope, but on Sundays we take the day off and we go around for hoping to see muskox. So this is a picture of our telescope in Greenland, which we have just finished building. This was built for the Event Horizon Telescope type of observation. It is actually involved in another very long baseline interferometric project called the GMVA, Global Millimeter VLBI Array, in addition to the Event Horizon Telescope at different frequency, 86 gigahertz instead of 230 gigahertz. So I want to clarify something that was mentioned a couple of times in the introduction, that the black hole image that was just released recently, the Greenland Telescope contributed to it. That is not actually true. That is going to happen next. The next image that we are about to release does have the data from the Greenland Telescope. The Greenland Telescope construction finished in the summer of 2017. Whereas the black hole image that was released on 10th April 2019, the data were obtained in April of 2017. So a few months before we finished building this. So the reason why we built this telescope in Greenland is that it provides the long baseline length. You remember I mentioned the angular resolution goes as lambda over the maximum distance. You actually want to have such a long baseline length, particularly along north-south direction, particularly for the source called M87. where this black hole was imaged. So this is the Greenland and submillimeter array and the ALMA telescope. Those pictures I showed you. So that forms a triangle of approximately 9,000 kilometers. And we are observing at wavelength of 1 millimeter. We are also using the South Pole telescope on this project. So that is the famous image of the black hole. I did not talk about it, even though this is more exciting. But I'm really excited to be part of this collaboration. And we are hoping that our telescope, which is currently at this Thule military air base in north here, will eventually arrive at this summit station where the atmospheric conditions are actually much better. This is the vehicle which is supposed to carry the telescope parts across the ice. So that's the end of my talk. Here is just a picture of me and Sonal with Bob Wilson in Homedale, where we visited him last year. With this famous horn antenna that was used to discover the 3 degree Kelvin CMB, cosmic microwave background radiation. And Bob is actually involved in undergrad education, and I'm very happy to be part of that class as well as an instructor. So we actually take undergrad students to this telescope. They put a receiver here at the focus, and they actually try to repeat this experiment. Thank you very much. Sorry, I may have gone a bit over time.